Okay, so we're going to talk about section 6.6, which is going to sound scary, but it's about inverse trig functions. Okay, so this is the opposite of trig functions. So you guys will all remember what the sine graph looks like. So this is +1 here, and this is -1 here. And sine looks like this. It goes down to -1, and then it's 0, and then it's up at 1, and it goes like that. Okay, so this is y equals sine of x. This value here is pi over 2, and this value here is minus pi over 2. Okay, so I want to point out that, okay, so sine doesn't pass the horizontal line test, right? Because if you draw a horizontal line, it intersects sine. If that line is between -1 and 1, it intersects sine in infinitely many places, right? It would just keep going and would just keep intersecting. But between minus pi over 2 and pi over 2, it does pass the horizontal line test. And so that is the domain of the inverse sine function. So the inverse sine function, sine inverse of x, this is how we write it. Y equals sine inverse of x. Sometimes we put the word arc in front of it and we say arc sine. So we either say sine inverse of x, okay, we say that, or we say arc sine. Okay, they mean exactly the same thing. So if y is equal to sine inverse of x, then that's the same thing as saying that sine of y is equal to x. Okay, so now how do we obtain the graph of this function? So again, this is the key relationship here. Y equals sine inverse of x means sine of y equals x. This, I can't emphasize enough, understanding this concept, which is our inverse function concept. This will carry you through this section. So the graph of sine inverse of x has as its domain -1 to 1. So -1 to 1 here. And at 1, it's at pi over 2, because that's where the sine function is. At pi over 2, it's at 1. So at 1, the sine inverse function is at pi over 2. And then at -1, it's at minus pi over 2. And it looks like this. Okay, so this is the graph of the inverse sine function. So this is y equals sine inverse of x. Okay, and you can see we obtained this graph just by taking this portion of the sine graph and reflecting it across the diagonal line at 45 degrees. So the domain of this function is equal to -1. It's the interval from -1 to 1, and the range is minus pi over 2 to pi. Okay, so or minus pi over 2 to pi over 2. So that's the inverse sine function. Okay, let's take a look at an example. So example, what is sine inverse of, let's say, a half? Okay. So what is this? Well, remember, I mean, so the normal input for sine is an angle. So the output for sine inverse should be an angle. So we usually call this an angle. Sine inverse of a half, we usually use the Greek letter theta to indicate an angle. So what does sine inverse of a half equals theta means? Well, it means that 1/2 is equal to the sine of theta. Okay, so what angle is it whose sine is a half? Okay, and so maybe you don't know this right off the top of your head, but the angle whose sine is a half is pi over 6. Okay, I don't expect you to know necessarily that sine of pi over 6 is a half. We'll give you tables and that sort of thing. What's more important is that you understand this process right here. Okay, so this is the answer. So sine inverse of a half is equal to pi over 6. Okay, very good. So the key notion here is that if you take sine inverse of sine of x, okay, this is sine, this is its inverse. So these two functions undo each other exactly the same way that log and e to the x undo each other. So the same thing is true if you take sine inverse of x and put that inside of the sine function, they undo each other. So they undo each other in both ways. They're inverse functions to each other. This is the key relationship about inverse functions. Okay, so let's do an example here where we simplify the tangent of sine inverse of a third. Okay, so what is this? Okay, so simplify. All right, well, this is an angle because it's the output of an inverse trig function, so we call it something. We call it theta. Okay, now here's how this goes. So sine inverse of 1/3 is equal to theta. That means that 1/3 is equal to the sine of theta. So sine inverse of a third equals theta means you move the sine over to the other side and we get this. Okay, now we take this relationship and we're going to draw just an abstract right-angled triangle. So here's a right angle. I'm going to put the angle theta there, and I want to label the sides of this so that the sine of this angle is 1/3. So sine is the opposite side over the hypotenuse, so we put a 1 there and a 3 there. So this triangle now has sine of this angle 1/3, which is a third. Okay, so we've drawn a triangle that has this as its sine. Now, how do you get this side right here? Well, you use the Pythagorean theorem. If you have a right angled triangle, then this length squared plus this length squared equals that length squared. So we can take the square root of 3 squared minus 1 squared, and that's the length of this side using the Pythagorean theorem. So that is root 8, or if you're fancy, it's 2 times root 2. Okay? So now that we know all the sides of this triangle, we can answer what is the tangent of it. So the tangent of theta is the tangent of sine inverse of a third, because that's how we defined theta. Theta was sine inverse of a third. And so the answer to this question is just the answer to what's the tangent of theta. The tangent of theta is just the opposite over the adjacent. So we get 1 over the 2 times the square root of 2. Okay, so this is the answer. Okay, anytime you see a trig function with an inverse trig function inside of it, this is the technique you use. Okay, so I encourage you to go back through the video here and really convince yourself that you understand how this went. Okay, so that's an example. Now let's see what else we got. Okay, so here's an opportunity for super bonus points. Super bonus proof. Okay, super bonus proof. If y is equal to the inverse sine of x, then question, what is the derivative of y? Okay, so we're going to go through and we're going to figure out what the derivative of the arcsine function is. Okay, so I'm going to use our relationship of inverse trig functions to write this equation in this way, right? Sine of inverse of x equals y means sine of y equals x. And now I'm going to take the derivative of both sides with respect to x here. So let's take the derivative of both of these with respect to x. On this side, we just get 1, right? Because the derivative of x with respect to x is just 1. Here, well, y is a function of x, and it's inside of the sine, so we have to use the chain rule. So we get cosine of y. Okay, that's the first part, that derivative of the outside function. And then we multiply by the derivative of what was inside. Okay, so we get this equation. Now this can be manipulated because we want to figure out what dy dx is. So we just divide over the cosine of y like this. And now I'm going to take this relationship here, and I'm going to rewrite cosine of y as the square root of 1 minus sine squared. Okay, this is using the fact that, of course, cosine squared y plus sine squared of y equals 1. Okay, sine squared plus cosine squared equals 1. So all we've done is we just replaced cosine of y by solving this for cosine of y. So we get that. Okay, but now remember, y, sine of y here is equal to x. So we've got sine y squared here, so this simplifies to be this. Okay, so that means that the derivative of sine inverse of x. So the derivative of this function is 1 over the square root of 1 minus x squared. Okay, so this is something you don't have to understand the proof, okay? But if you do, super bonus points. I'll ask you to prove it on a future exam. But you should know this. In particular, this means that if you want to integrate 1 over 1 minus x, or 1 over the square root of 1 minus x squared, then this is the inverse sine function of x plus c. Okay, so know these two things. All right, so that is the proof, the justification for the fact that sine inverse of x's derivative is 1 over the square root of 1 minus x squared. Okay, let's move on to cosine inverse. So this is cosine inverse, or arc cosine, same thing as before with sine. Let me write it this way. And what it means is it means that cosine of y is equal to x. So this is the relationship between cosine and its inverse function. Again, if you have cosine inverse of x, then these two functions undo each other, so you get x back. And if you have cosine inverse of cosine of x, then these two functions also undo each other. Cosine and cosine inverse undo each other. So this is the inverse relationship between the two of them. The derivative of this function, okay, is equal to, looks a lot like the derivative of the inverse sine function. It's just minus the derivative of the inverse sine function. And the graph of this function is looks very similar to the inverse sine function. It has a domain. You get the graph of this from excuse me, from flipping the graph of cosine across the line y equals x. It looks like this. Okay, and this height right here is pi. This is pi over 2, and this is 0. So the domain is, again, minus 1 to 1, and the range is from 0 to pi. Okay, that's the inverse cosine function. Let's take a look at the inverse tangent function. This will be the last of our inverse trig functions that we'll think about. So y equals the inverse tangent function. Okay, this is called arctangent as well, arctangent of x. And what this means, same as with sine and cosine, is it means that the tangent of y is equal to x. Okay, the graph of tangent looks like this. So tangent of x has vertical asymptotes at minus pi over 2 and pi over 2, and it looks like this. Okay, and so this is tangent. So the inverse tangent is what you get when you take this and you flip it. Okay, so these vertical asymptotes will turn into horizontal asymptotes, and so we'll get a horizontal asymptote at pi over 2, a horizontal asymptote at minus pi over 2, and then the inverse tangent function goes like this. Okay, so notice, so this is arctangent. Arctangent, tangent inverse, they're the same thing. So notice what this means. This means that the limit as x goes to infinity of the inverse tangent function is pi over 2, and it means the limit as x goes to minus infinity of the inverse tangent function, or arctangent, is minus pi over 2. Okay, so it has these behaviors. Its graph behaves like this. All right, so that's the inverse tangent function. So let's do an example where we simplify the following. So cosine of the inverse tangent of x. Let's simplify this. Okay. Now this will look very similar to the to what we did for the sine inverse of a half, or of a third. So if we take if we take this, remember the output of an inverse trig function is an angle, so we call it an angle here. So we get theta is equal to the inverse tangent of x. That means for us that the tangent of theta is equal to x. And now I want to take this and draw a right-angled triangle that has an angle theta here, and I want the tangent of that angle to be x. Well, the tangent is the opposite over the adjacent, and so I'm just going to label these x and 1 because x over 1 is the tangent of that, and that's what we have, the relationship we have written here. Now again, we use the Pythagorean theorem, so this length right here should be 1 plus x squared. You take 1 squared plus x squared, add, then you take the square root to get the length of the hypotenuse. And now this allows you to say what the cosine of this angle is. The cosine of this angle is the cosine of the inverse tangent of x, because theta is the inverse tangent of x, and that's what we're trying to do. So the cosine of that angle is the adjacent side over the hypotenuse. So this is 1 over the square root of 1 plus x squared. This. So that's so this is the answer. We've simplified this so that the cosine, well, we have it right here. So this is that simplified. All right, let's take a look at a few other examples. So so a fact here. The derivative of the inverse tangent function, this can be derived in exactly the same way that the derivative of the inverse sine function can be derived, and if you do that, you will get 1 over 1 plus x squared. So that means in particular that if you integrate 1 over 1 plus x squared, what you get is you get the arctangent of x plus c. So these are the formulas. You know, as an exercise, you should try to apply the same super bonus proof that we did before in the case of sine. If you can understand how to figure out that the derivative of this function is actually that, then you're really doing well at understanding this. So now let's do one example, and then we'll be done with this section. So I want to integrate the following quantity, 1 over x squared plus 9. Okay. It's not 1 over x squared plus 1. It looks a lot like it, and so its integral should probably look a lot like arctangent, but it's not quite there yet. So I'm going to show you a trick. Okay, trick. Okay, this is a trick. I'm going to factor this 9 out of here. So we get, so if I pull a 9 from here, then I will have x squared over 9, and then plus 1, like that. Okay, just a little trick. Factor out the 9 from there. So let's pull this 1/9 out of here, and I want to rewrite this in a way that's going to help us solve this integral. X squared over 9 is the quantity x over 3 squared. Okay, so we'll do that. You'll understand why this works in just a minute, because now I want to use a substitution. Now this is really starting to look like the derivative of arctangent, and so we just have to make a simple substitution here, and that substitution is that, x over 3. So du is equal to 1/3 dx, which means that 3 du, we write that everywhere we see dx. Okay, so let's rewrite this integral then. We get 1/9 on the outside, 1 over u squared plus 1, and then everywhere we see dx we write 3 du, so we have, there's really a 3 and a du here. Looks silly, but that's just a 3, so it cancels with one copy of the 3 there, and we get 1/3 1 over u squared plus 1 du, and now this here is equal to the arctangent of u, which will be 1/3 the arctangent of u plus c. We're not quite done because u is equal to x over 3, and so we get 1/3 the arctangent of x over 3 plus c. And this is our answer. Please tell me that shows up on the camera. It does indeed show up on the camera. Okay, that's the end of the inverse trig functions. Nothing too mysterious here, so we'll work on these in class, and class will hopefully get to know and get to love the trig functions. Okay, great.